All right, here in this walkthrough, we're going to cover breaking down a FAT32 file system. Specifically, we're going to cover the BIOS perimeter block, or otherwise known as the volume boot record. To get started with this, I had previously created a FAT32 training system, and we're going to also bring in the positions I marked up for the master boot record for a little bit of efficiency. For this particular walkthrough, we're going to be using the boot sector section out of our reading analysis and some other online guides. Particularly, we're going to be focusing on table 10.1 and table 10.3 for our work. As we've learned through our reading, there's a lot of similar structures between each iteration or version of the FAT32, FAT16, and FAT12 file system, but particularly with FAT32, there's an expansion or extended BIOS perimeter block that contains a little bit more information. And that's okay, we're going to continue working on that here. So starting here, looking at our master boot record, we can see that if we scoot down to our first partition entry, because that's all we see here, is for a 4-byte sweep, our starting LBA sector offset tells us that we need to go to sector 128 to be able to navigate down to our BIOS perimeter block. Clicking here, we're going to type in 128, and here we are. Now, there's a lot of important structures when it comes to breaking down the volume boot record BIOS perimeter block of the FAT32 file system. At this introductory level here, as we start to get our feet in our ground underneath us when we're talking about this file system, we're going to cover a few important structures that are critical for you to be able to get an understanding of how this file system works. Again, there's a lot of these different structures. We're going to cover a few of these in a little bit more detail. So our first important structure that we're going to work to cover is the bytes per sector, a very critical part and component of understanding how data is stored in and how many sectors and clusters are being used to hold data within a particular file system. Now in our guide here, that's referenced as byte range 11 through 12. Some guides may also reference that as offset 0B for a total length of 2 bytes. So remember, as we're walking through, we may switch back and forth between hex offset ranges and byte ranges. So 11 through 12 would start at 0 and move to 11 because we know that 0 through 9, A through F, 0 through 9, that would be 10, that would be 11. So that's why it's also references offset 0B. We can also see that at the bottom here in our screen. If we switch to decimal view, that might be a little bit more applicable to our current table that we're working with. So range 11B, it will give us bytes per sector. So we can see here in our data interpreter that that would be 512. So that means that there are 512 bytes per individual sector. And as we learned in data structures last week, sectors are the smallest building block or component within a storage medium like a hard drive or a USB drive that's recognizable by the storage drive. You can definitely have a file that's 400 bytes, and that will be stored within a single 512 byte sector. You'd have just a little bit left over, and that's called slack. We'll talk about slack in a different block. But just know that there are 512 bytes per sector, and we learn that starting at byte range 11 through 12, or offset 0B. Now the next important structure here is the sectors per cluster. This is at byte range 13 through 13, which means it's only 1 byte in total length. It starts at offset 0D. Again, swapping to decimal, we can see it here. Taking a look at our data interpreter for 8 bits, we can see that it is 2. So that means there are 2 sectors per cluster. So with these 2 components, you know how many bytes per sector and how many sectors per cluster. This is a really important aspect of understanding how data is stored and laid out and how it's kind of quantified across a storage medium. So if you're faced with the task of having to recover a 1000 byte file from this particular file system, we are already armed with some knowledge to be able to gain an understanding of how many sectors or clusters are needed to be able to accomplish that particular job. So we know from offset 0b for a total length of 2 bytes, we're dealing with 512 bytes per sector, and we also know that there are 2 sectors per cluster. So if we had to recover that 1000 byte file, we would be looking at a total of 2 sectors to be able to recover that, because they only go in multiples and their only allowed values are something like 512, 1024, 2048, 4096, 8192, so on and so forth. So you can only go in multiples. So because of that, that 1000 byte file would actually be assigned 2 sectors, not 1000 bytes, 2 total sectors. If the question was reframed slightly differently, and it was how many clusters are needed to hold a 1000 byte file, well, we can note here that there are 2 sectors per cluster, so that answer would actually be 1. You would need 1 cluster to be able to hold on to a 1000 byte file, because there are 512 bytes per sector. And we know that a cluster has 2 sectors assigned to it.